Hey guys, this is Mrs. Hunter, and you are watching part 2 of the Unit 10 Lecture 4 discussion on solubility equilibria. So, let's first start by talking about what we're going to cover in this part of the lecture. So, we have already spoken about what solubility equilibria is and how we can write a Ksp expression. And so what we're going to look at in this lecture is, if you're given data, how can you solve for Ksp? And we're also going to look at, if you have a Ksp value given to you, can you figure out the concentration of the respective ions in a solution? So, can you solve for molar solubility when you are given Ksp? All right, let's start. All right, so let's take a look at this first example. We want to calculate the Ksp if the lead ion concentration of dissolved lead 2 chloride is found to be 1.62 times 10 to the negative second. Okay, so we have lead 2 chloride, and they've given you the lead ion concentration of this. So first, let's think about that, right? So lead plus 2 chloride, right, minus 1, so I'm going to need 2 of those chlorines. And when it breaks apart, and I'm just going to do this the quick way, it's going to break into the lead ion and 2, hit the button, my bad, 2 of those chlorine ions. So, if the lead ion concentration is 1.62 times 10 to the negative second, and we can see from the balanced equation that we should always have 2 chloride ions for every 1 lead ion, we know that the concentration of the chloride should be double the concentration of the lead. So if you think about it like not a full-blown ice table, but just think about it in stoichiometric proportions. If this is X, then the chloride needs to be 2 times X. And we know what X is, right? So this is just kind of like stoic stuff. So we know that the Ksp expression for this, excuse me, is the concentration of the lead ion times the concentration of the chloride ion squared. So we have concentration of lead. We also, because of stoichiometry, know what the concentration of chloride should be. So we can figure out the Ksp from here. So concentration of lead, 1.62 times 10 to the negative second times the concentration of the chloride squared. Okay, so to get the concentration of the chloride here, right, so we're going to multiply the concentration of the lead ion by 2. Okay, I'll put some extra parentheses so this gets less confusing. And then whatever that is, we're going to square it. So let's go ahead and put this in our calculator. So 1.62 times 10 to the negative second. Make sure you close and do all your parentheses, times 2 times 1.62 times 10 to the negative second. Close that parentheses. Right, I want to square that value. And then you should get 1.70 blah blah blah. So I'm going to round to 3 sig figs. So this is going to be 1.70 times 10 to the negative fifth. Do you guys get this? So let's try another example, and this time I'm going to give you guys a little time to try and solve it before I give away the answer. So a little hint, when you see this measured solubility phrase, that is a fancy way of saying the concentration of the solid. So copper 1 bromide has a measured solubility of 2.0 times 10 to the negative 4th moles per liter at 25 degrees Celsius. Calculate its Ksp. All right, give that a try. Okay, did you get 4.0 times 10 to the negative 8th? If you take a look at the work, if we know the concentration of even one of these, right, we know that because they're a 1-to-1 ratio, that they both have the same concentration. So 2.0 times 10 to the negative 4th, you could have even times 2.0 times 10 to the negative 4th, you could have just taken 2.0 times 10 to the negative 4th squared, and hopefully you can see this is a great kind of problem that you could see on multiple choice because you don't even need your calculator, right? 2 times 2 is 4, and then when you multiply exponents, right, you're adding them together, so you get negative 8. How'd you do? All right, so Ksp values are actually a lot of times given to you in a table and whatnot, and you kind of need to be able to understand and interpret them, which isn't the most common thing we do with them, but as long as they have the same ion to ion ratio, you can actually compare, right? The main thing we're going to use them for, however, is going backwards. So those problems we just did, right? Instead of solving for Ksp, we're going to go backwards and try and solve for that measured solubility value. So let's look at an example. All right, so this is an example that we did earlier. We actually found the Ksp expression for calcium fluoride. So I looked at a table and found that the actual Ksp value for calcium fluoride is 4.0 times 10 to the negative 11th. And we want to know what is the molar solubility of that. All right, so let's try it. So we know that the Ksp for this, the expression is going to be concentration of calcium ions times the concentration of fluoride ions squared. Okay, and this will equal 4.0 times 10 to the negative 11th. All right, so you are essentially solving for x. And if you think about it, right, you had that dissociation equation that we wrote earlier. For every 1 calcium, there should be 2 times that value of fluorine. So imagine we rewrote this now, right? 4.0 times 10 to the negative 11th is equal to x times 2x, right? Because the concentration of fluorine would be doubled, and we still have to square it because that's part of the equilibrium expression. So now you have an equation that we can just solve algebraically, right? So if we start to solve this out, you have x times 4x squared, and so that's I'm gonna jump down a line so this looks a little better. 4 times 10 to the negative 11th is equal to 4x cubed, right? So we can divide both sides by 4, and you should hopefully be able to do that, right? That's 1.0 times 10 to the negative 11th is equal to x cubed. And now when you have something cubed, we can take the cubed square root of it. So ask your neighbor if you don't know where to find this function in your calculator, but you can do the cubed root of 1 times 10 to the negative 11th, right? And when we do that, I got, give me a second, let me do that. When I did that, I got 2.15, so I'm going to round that to 2, and that's supposed to be a decimal. Sometimes the circular dots are not easy on this. So 2.2 times 10 to the negative 4th. Right? And that is our value of x, and that is our molar solubility. So what do you think? Let's try another one. So the Ksp value for copper to iodate is 1.4 times 10 to the negative 7th at 25 degrees Celsius. Calculate its solubility at 25 degrees Celsius. So I'm going to give you guys a little bit of time to solve this. Alright, so you have copper iodate. It's going to break apart into one copper ion and two iodate ions. So if we think about this, right, for every one of those, you get two of those. So when we think about Ksp, right, which the Ksp value is given to us, that's going to be equal to concentration of copper ions times the concentration of iodate ions squared. So essentially you have 1.4 times 10 to the negative 7 is equal to x times 2x squared, which you know that we can simplify that just like we did last time, right? 2x squared. Oop, that square should be on the outside. That makes that different. So 2x squared gives you 4x squared times x, so right, that's 4x cubed. So if we want to figure out x, I'm going to save a few steps from last time. We are going to do the cubed root of 1.4 times 10 to the negative 7th divided by 4. And I am confident you guys got 3.3 times 10 to the negative 3rd molarity or moles per liter. So hopefully you were feeling good about this. I am going to pause the video here and go take my puppies for a walk. This, by the way, is a video of them when they were hanging out with me on conference night a few weeks ago. Yeah, I know, adorbs. All right, so join me for part 3 in just a little bit.